Well, the curious thing about the brain is that it's hiding in plain sight.
Sooner or later, humans have to confront the fact that we don't know how the brain works.
The Brain Mapping Center in Los Angeles offers its customers powerful brain imaging technologies. High-power magnetic scanners have become an invaluable diagnostic tool and produce images to marvel at. But leading neuroscientists are saying, if you think these technologies reveal how the brain works, think again.
We do a great deal of neuroimaging today, CAT scanning and MEG and EEG and so on. And all of this imaging today is substantially blind to the true connectional anatomy of the human brain.
You cannot take normal subjects and open up their head to look at their brains. That's not practical. You have to look at it with the technologies that you have, and by doing that, you're one step removed from reality.
Within a square millimetre of the brain, a dense maze of millions of neurons may be firing away. To depict this process with animation and computer graphics is one thing. To capture the reality has been a daunting challenge.
Every single neuron, pretty much, is unique, has its own wiring diagram. And that is, there's no simple redundancy of just having a lot of the same unit. And that's why the brain has been so much more intractable to understand than other organ systems.
The connectivity of the brain is crucial to its function. All of the operation of the brain occurs upon a substrate of its physical connections.
Jeff Lichtman and his colleagues at Harvard University have been pioneering techniques for brain circuit imaging.
One of the fundamental questions that has plagued the field of neurobiology, which is, what is the physical substrate of memory? Where is your memory of your grandmother in your brain? In what form does it sit? What is the physical instantiation of your grandmother? A lot of people would say it is a wiring diagram.
Neuroscientists at Harvard are perfecting a technology which they hope one day will map a human memory. This scanning electron microscope has been imaging neural pathways of mice and rats from slices of their brains.
This is a half of a rat brain that has been fixed with chemical fixatives and embedded in plastic so that it can be sectioned very thin.
And the piece of kit doing the brain slicing is called an automatic tape-collecting lathe ultramicrotome.
In order for an electron microscope to trace neural circuits, it has to be able to see those neural circuits on the surface.
This assembly line brain slicer requires a spool of film with an electric charge to attract and secure the ultra-thin slices.
So these slices are on the order of about 30 nanometers in thickness. And to put that in perspective, human hair is about 50,000 nanometers in thickness.
I believe we want to look at the smallest resolution, every last bit of it. This is a brain, this is that hippocampus part of the brain of a rodent, and that's the size of one of these sections. They're really massive for the electron microscope. That's the slab that these images came out of. So we've magnified up here many thousands of times to get images like this. This object here, this little circle, is about 40 nanometers in diameter. That's 400 hydrogen atoms wide, so it's pretty small. This is a synapse. At high power is basically the ground truth of what's in there. So now you're looking now at full resolution at all the synapses in one very, very small part of that big data set.
Because of the density of neurons, inventive strategies are required to clearly see and trace pathways.
You can trace out one process over a long distance.
In this instance, one of Jeff Lichtman's students meticulously coloured by hand the individual neural fibers.
Pick up off of that. And once you do that, then it's not hard to do it for lots of processes in the same data set.